So let us continue our design example, this time with a Mealy-type architecture. So if you recall, in a Mealy-type architecture, the output is a function of the current state as well as the current input. Okay, so the way we draw the FSM is also different. The output values are specified on the transition arcs going from one state to the other, okay, and not on the state itself. So let's see what the Mealy-type finite state machine will look like for this example. So we were detecting the sequence 1 0 1 1, right? So let's see, initially on any reset we enter the reset state. Let me rename it as state 0. We'll give it some names, but enters a reset state. So this is a reset state. When we receive a 1, we enter a state and remember that we have received a 1. Next we are expecting a 0. So in the state we have received a 1 and a 0 so far. Then if we receive a 1, we have entered a state 1 0 1. And now what are we expecting? We are expecting 1. But this is a Mealy-type finite state machine and the outputs can be specified on the arcs itself. So I can assert the output value y equal to 1 and move directly to the next state, right? I don't have to have a state corresponding to 1 0 1 1, right? So let me denote the outputs here in blue. So on this arc the output is 0, output is 0, output is 0, and now the output should be 1. But which state do we go to? When we have 1 0 1 1, remember that we could get inputs like this 1 0 1 1 and then 0 1 1. So this is a valid sequence and this is also a valid sequence. So we expect the output to be asserted at this point and also at this point, right? So this 1, after getting this 1, we should not go back to the reset state, but rather treat this as a 1 was received for the next sequence, potentially the next sequence, right? So if we receive a 1, further we go back to the state 1 and not reset. So if we receive a 1, then we assert the output y equal to 1 and we go back to the state. Okay, so far so good. Okay, so let's complete this state machine. Let me label the states. Let me call the state 0, state 1, state 2 and state 3. So okay, so let's complete this state machine. So if I am on state 0 and if a 0 input is received, then go back to the same state and the output is 0. If in the state 0 is received, you go to the next state, but if a 1 is received, we stay in the same state. So on a 1 we stay in the same state. Now in this state, state 2, if we receive a 1, we go to the next state, but if we receive a 0, then what do we do? Because we have received so far a 1 0 and then a 0, right? This is not a valid sequence, so we should go back to the reset state. Is that right? Okay, yes. So if we receive a 0 in this state, we go back to the reset state, right? So on a 0 we go back here. Now coming to the last state, if we get a 1, we go back here. What about if we get a 0? So notice that in this state we have received so far a 1 0 1 and now we receive a 0. This could be considered, these last two values could be considered as a potential beginning for the next sequence, potentially. So we should go back to the sequence state where we remember that we have received a 1 and a 0, right? So if we get a 0 here, then we go back to state 2. So the output is a 0 on all of the transition arcs except for the one here. So let me just denote that, and we are done. This is our Mealy-type finite state machine. So here is the final state machine that we get. So make sure that this FSM representation is complete. Okay, each input combination is represented for each of the states. Right. So now, what would be the difference between the Mealy-type and the Moore-type state machine? Okay. So first of all, in a Mealy-type state machine, the output is a function of the state as well as the input, sure. Okay. Secondly, the output value is sampled a little before the clock edge. Okay. So the output value is valid, or the valid output value is to be read slightly before the rising clock edge in this example. So let us now see how we can design a circuit corresponding to this Mealy-type finite state machine. The first question is, how do we encode the state? Okay, we have to decide upon a state encoding. So we have 4 states, right? So we need at least 2 flip-flops. So let's say we use a simple binary encoding for the state. State 0 is just 0 0, state 1 is 0 1, state 2 is 1 0, and state 3 is 1 1. So if we have fixed the state encoding, we can build a state table. So let's go ahead and do that. What will our state transition table have? Okay, so here's the input. Let's call this bit Q1 and this Q0. So at time t, the value of Q1 and Q0 and the input together determine what should be the next state. So Q1 and Q0 at time t plus 1, and the value of the output y. So let's list down all the combinations. So let's fill up this table state by state. Let's start from state 0. If we get an input 0, we go back to the same state and the output is a 0. But if we get an input 1, we go to the next state, output is still 0. On the next state, state 1, if we get a 1, we go back to the same state. So on input 1, we go back to the same state, 0 1, output is 0. But if we get a 0, we go to the next state, which is 2. So on an input a equal to 0 and state 0 1, the next state is 1 0, output is still 0. Okay, so now let's consider state 2. If we get a 0, now we go back to the reset state. So if the state is 1 0 and if the input is 0, we go back to the reset state. So Q1 Q0 are 0 0 and output is 0. But if we get a 1, then we go to the next state. So we go to state 1 1, right? We go to state 1 1. And finally, if we consider state 1 1, on a 0 input, we go to state 1 0. But on a 1 input, that is this case, we go to state 1 0 1, and here the output is asserted y. Okay, so we have our state transition table. Let's try to simplify this. Okay, so let's take Q1. So Q1 consists of the minterms. It has 4 minterms, right? So this is 0 1 2 3, so it has the minterms 4 5 6 and 7. Oh sorry, this is Q0. Q naught has the minterms 4, 5, 6 and 7. It is 1 for these minterms. Okay. Then we have Q1. Q1, which has the minterms, well, it has 1, 2 and 3 minterms. Okay, that is minterm 1, 3 and 6. And finally we have Y, which is just one minterm. So it is just one minterm, which is 7. So can we derive the Boolean expression for these terms? Yes. Okay. So let's derive the Boolean expression. So Q naught is all ones for this. So it's very simply it is equal to A. You don't have to use a Karnaugh map. It's obvious that all combinations of Q1 and Q naught are present and A is 1. So this is A. What about Q1? If you simplify it, you get the expression for Q1 as A bar Q naught or A Q1 Q naught bar. So since this is just a 3 variables system, you can use a Karnaugh map or you can use a solver, Quine-McCluskey solver or some other solver. Okay, and Y is simply just this one term, so it is A, Q1 and Q naught. So we have got the Boolean expressions for the next state and the output, right? So what would our circuit look like? Okay, well, we have 2 flip-flops. Let's assume that their clock inputs are connected together. Okay, and let's say this is Q naught and this is Q1. What is the input for this flip-flop Q naught? It's A. Alright, what is the input for the next flip-flop Q1? It is, I'm not drawing the logic diagram here, it's some combinational circuit which is actually just not A, Q naught or A, Q1, Q naught bar. So essentially we have some combinational circuit which is giving this, and it is taking values from Q naught and Q1 and A. And finally we have Y, which is simply an AND of all these things. So the output Y is just A and Q naught and Q1. So we have arrived at this logic circuit for implementing our sequence detector. Let's see if it works. We can test it by writing a VHDL structural description corresponding to this circuit using D flip-flops and checking if it works, simulating it. So here is the code for the structural description. So here's the code for the structural description. Okay, in EDA playground. So we first describe a D flip-flop as usual, and then this is the sequence detector with the same interface as before. Okay, and then we instantiate 2 flip-flops, DFF1 and DFF0. Okay, to the first flip-flop's input we just connect A. To the second flip-flop's input we connect this Boolean expression, just same as the Boolean expression that we derived, and finally this is the expression for Y. Straightforward. Now let's see the test bench. test bench is slightly different. Okay, so what we want is, we want the input value to be valid slightly after the clock edge to simulate real circuits, right? Because the input is going to be valid slightly after the clock edge. So what we do is, we create a clock signal, and we create a signal A0 which is synchronous with clock. This value is changing exactly with clock. Okay, if you notice, clock has a time period of 10 nanoseconds, and the signal A0 is changing also after 10 nanoseconds, and I assigned some sequence. Okay, so 0 1 1 0 1 1 0 and so on, like this. And now I want to create a slightly delayed version of this. So I say A is A0 after 1 nanosecond. So A is a slightly delayed version of A0. So what I have is a signal whose sequence I have provided, okay, like this, and its value changes slightly after the rising clock edge. And I will feed in this value to the circuit, and the valid output Y is to be sampled slightly before the clock edge. Okay, that's what we do in a Mealy-type state machine, right? The output is valid slightly before the clock edge. So let's see what the waveform looks like. So here is the output waveform. Okay, first thing to notice is that, okay, initially this system is reset and we are in state 0. So this is showing the reset waveform, clock, input waveform A, Y, and the state. So initially we are in state 0. Okay, then we go to state 1, then we go to state 2, 3, okay, and finally whenever we go from state 3 to state 1 on that edge, whenever there is a transition from state 3 to state 1, the output Y is asserted. So here is the output Y being asserted. If you look at our state machine again, the output is asserted only whenever we are going from state 3 to state 1. Everywhere else it should be 0. So if you notice, that is indeed happening. Y is 1. There's a wide pulse when we are going from state 3 to state 1. But if you notice, there is a small glitch here occurring here and here. Why is that occurring? So what is happening here is that we are in state 3. Okay, so on this clock edge you are in state 2, and the next state is state 3. Okay, so for this period the next state is 3, and the input is actually 0, but it takes slight amount of time, right? The input value changes slightly after the rising clock edge. So what happens is, for a brief period there, okay, the input value is 1 and the state is 3, and that is our condition for asserting the output Y. So there is a small glitch appearing at the output, but it doesn't have any effect on the next state, but it's a glitch that appears on the output. This is the issue with Mealy-type designs, where you have a direct path from the input to the output going through combinational logic. Okay, so we see two small glitches. This is happening because the input is slightly delayed. Okay, for a short period after the clock edge, the input value is still 1. It takes a little time for it to go to 0. So actually the input is 0 in this clock period, right? So from state 3 you have an input 0, so you should be going next to state 2. But for a brief period the output is asserted, although our state change does not happen. The next state change will only happen on the next rising clock edge, which is 2. So this state change is fine, but only effect is that on the output pin we have these small glitches. Otherwise this waveform is identical to what we would have got in the Moore type of state machine, except these glitches. And also of course that there being a delay between the input and the output, because it's going through a flip-flop. So the code for this example is available on this URL. You can go and explore this code, try running the simulation and try understanding the state transitions and check if you're convinced that the state transitions will occur correctly. Okay. Now we will see how we can describe these state machines behaviorally in VHDL. So far what we saw were structural descriptions. That means you first take the state machine and solve the design problem, design a logic circuit corresponding to that state machine. So in that design process, the designer has to choose the state encoding, what kind of encoding you would use for the states, right? Once you make that choice and you write out the state transition table, you arrive at the Boolean expressions for the next state and the output. And once you do that, you come to a logic circuit that can be described structurally using VHDL, using the flip-flops as components. But there is a way to describe such state machines in a behavioral manner without going through the design process, directly from a state transition diagram. Okay, and there are synthesis tools which allow for direct or automatic conversion of such descriptions to a logic circuit. So let's see an example of how we could describe the same state machine in VHDL. So here is a VHDL code. Okay, we are going to use the process block. So whenever you are asked to use a behavioral description or write a behavioral description, it's mostly a process block that you will have to use, right? So in the architecture, we declare a signal Q of type standard logic vector 1 down to 0. So that means 2-bit, which encodes the state. Okay. Note that it's possible to do this without deciding what should be the state encoding also. You can just have an abstract type for the state, say state type is S1, S2 and so on. There is this way, there are multiple solutions to this problem. So we are just looking at one possible solution where the state encoding is assumed. Okay. So we initialize this 2-bit signal to 0 and we have then a process block. So this is one process block which computes what should be the next state and updates it. And here is another concurrent statement, a separate concurrent statement which updates the output based on the state and the input. So let's look at this process block. The sensitivity list of this process block consists of the reset pin and clock. We do not have A in the sensitivity list because even if the input changes, the state is not updated. The next state is updated only if there is a reset or if there is a clock, a rising edge on the clock, right? So let's go through this. So first we use the if else block. So if there is a reset, then the state is 0, 0. So reset has priority. But if reset is 0, then only if there is a rising edge on the clock, then what we do further depends on what state we are in, right? So the current state determines what would be the next state and the output value. So what here we calculate is just the next state. We use a case block in VHDL. So a case block in VHDL is somewhat similar to a case statement in C, if you have studied that. It just lists out all the cases and the actions to be performed or the sequence of steps to be taken when that case is met, and these are evaluated one after the other. So all of these code is sequential code inside the process block. So case Q is, so depending on the value of Q, whether it is 0, 0, if it is 0, 0, then we do this, else this and so on. Okay, so we specify one by one for all possible values of Q what should happen. So if the state is 0, 0, we again use a nested if else block within this case block. So the syntax is case something is, when, condition, and then here you can have some sequential statements. So our sequential statements are this if block. So if input is 0, then the next state is 0. Else if the input is 1, the next state is 0, 1. End if. Similarly, if the state is 0 1, and if the input is 0, then the next state is 1 0, else the next state is 0 1, and so on. So we essentially have converted the pictorial description of our state transition diagram into this VHDL process statement using the case construct and the if-else construct. So this is a way of specifying the default case. So when the current state does not match any of them, then what should be the action taken? So this is mandatory in the description. Okay. Why would it not match any of these? Because this is a standard logic type. So it could take values such as x or u, which it would not match any of these 4 cases given here. Okay. So it's mandatory. So this is straightforward. So this is just computing the next state. And then we have a separate concurrent statement which says that output should be an AND of A, Q1 and Q0. Could we have added this statement here itself? So for example, when 0 0, if A is 0, Q is 0, could we have added the statement A is assigned some value here, say 0? We could have, but that would be wrong. If we don't have an independent statement here, a concurrent statement updating the value of A, remember this entire process block is activated only on this condition, on the sensitivity list. So only when there is a clock edge will the output be updated. So if we had written the updates for output here, for example, y should be assigned a 0 here, this will not take effect instantaneously. Whenever there is a change on A, we want input A, we want the output to be updated, right? But if we write it here, this process block is activated only on a rising clock edge. So this would be like a Moore type of a machine inadvertently. Unintentionally, we would create something like a Moore machine here, right? We want the output to be updated as soon as the input is updated. So that's why we have a separate statement here which just updates the output as a function of the current value of the input and the state. So again, this code is provided for you at this URL. Please explore the code, see the test bench. The test bench for this will be identical to the one for the previous example. Okay, and you can check that the simulation result for the two descriptions is exactly the same. So with this, we have seen through an example of a sequence detector how we can arrive at the state machine for Moore type and Mealy-type architectures, and how we can arrive at a circuit, and how we can simulate those circuits structurally using VHDL. We also saw that if given a state machine, we can directly convert it into a VHDL description without going through the process of designing the logic circuit, arriving at the Boolean expressions for the inputs to the flip-flops and so on. Okay, we can describe such state machines directly in VHDL, and a synthesis tool essentially does something similar to what we have done in the design process. Okay, synthesis tool may arrive at a state encoding, may decide what encoding should be used for the state, and then arrive at the Boolean expressions for the inputs to the flip-flops in the circuit. So there is a way to directly describe state machines in VHDL and simulate them. However, if you are asked to go through the design process and write a structural description, then you should not describe it like this, but rather go through the design process, arrive at the circuit, and then describe that circuit in VHDL. If you are asked to write a behavioral description of the state machine, you can use these case constructs.